Hey, you should try this one a little bit on your own first before you just watch me do all the work. Try it, see what you can do. But here's the idea. This time we've got a density function. It's a spherical solid of radius 2. Let's just stop there for a minute. Can you imagine like a little spherical, like a metal ball, or I don't know what it would be, a radius 2 units. Let's see, maybe we got centimeters going on. So maybe a little metal ball or a ping pong ball. I don't know. I'm trying to just get a visual of what this might be, but a spherical solid. So it's not a ping pong ball because it's solid, but a solid of radius 2. And this solid has a density that varies with rho. Remember our Greek letter rho right there. Our Greek letter rho is the distance from the center of the sphere to any point on the edge of the sphere. So as rho increases, like notice when rho is 0, the very center of the sphere, 4 times 0 is 0, 0 grams per cubic centimeter. There's 0 density at the very, very, very center point. But as rho increases from 0 to 1, ultimately to 2, this spherical object gets more and more dense. But it gets even better. We're going to calculate the mass of the portion of the sphere lying above the plane. So now imagine the sphere. We're essentially going to like chop off the top of the sphere. We're only going to consider this top cap of the sphere, where this plane, the flat plane z equals the square root of 3, is like slicing off the top of this spherical solid, and we're only going to think about the mass of that part of the sphere. All right, well, to get mass in a situation like this, we're going to have to sum up. Now, the reason we have to sum up is because the density changes. See, it would be easy. If the density was the same throughout, we would just take the density times the volume, story's over. But it's not that way. The mass changes according to rho. The mass is 4 times rho. And I always like to keep track of my units. 4 times rho, the density was measured in grams per cubic centimeter. So in order to get mass in grams, we would have to multiply that by a volume. That is a dV. So imagine breaking this thing up into little tiny, if I could start with a little change in X, a little change in Y, a little change in Z. Can you imagine a little cubical thing here? Or not cubical necessarily, but rectangular solid in there. So tiny, infinitely many, infinitesimally small dx, dy, dz's inside of that thing. That's what dV would be, and it would be measured in a volume of cubic centimeters. And so this product is certainly going to give you some number of grams, as we would want. And we're going to define that over, did they give us a letter for it? Sometimes they give us like an E or a W or something. I don't know why they like those kind of letters, but we'll use W. So over this boundary, just that cap of the sphere, that's W. We're going to sum up the changing densities. As rho changes, the density is going to change. And we're going to multiply that by that infinitesimal volume for that set value of rho, theoretically, as we work through the integration. And that product is going to sum up some stuff to get the mass of the top of that sphere. All right, so this is where we can take advantage of what we now know about the different coordinate systems. Because this is a cap of a sphere, I believe that you'll find that the spherical coordinate system will be the most efficient way to work on this thing. 4 times rho times dV. Now, from the videos, and we're going to do some more work on this later, but from the videos, it was said that dV, which is dx, dy, dz, in the rectangular system, turns out to be rho squared sine phi d rho d theta d phi. So this thing right here is dV. Remember, in cubic centimeters. this thing right here is the density in grams per cubic centimeter, and that product is still going to get us the mass in grams. All right, now we're going to do some more work on this, but remember r d theta? Kind of like that, in spherical coordinates, dv comes out to be rho squared sine phi, d rho, d theta, d phi. All right, so let's work on setting this thing up and continuing the process. Let's talk about rho first. So rho varies from what to what? Now, as you've seen throughout this module, I keep trying to highlight the error in thinking. Here's what people would want to do so often in this case. Let me get rid of my, ooh, that didn't get rid of it. Yikes. Put using my pen maybe. There we go. The problem would be this. So many people want to say, well, rho varies from the square root of 3 to 2. Because remember, rho was 2. So the radius of this sphere was 2 units. The cap of the sphere got cut off when z is the square root of 3. So many times people will say rho changes from square root of 3 to 2. No. Rho is 2 here, yes. Z is the square root of 3 here, yes. But z is the square root of 3. Now, what about, say, here? What if we came out and we talked about this segment right here? In this segment right here, would rho still be the square root of 3 to 2? Or how about if we came out here? Would rho still be the square root of 3 to 2? Or how about right here at the edge, would rho still be? Now remember, rho is measuring a distance from the center, from the origin. So yeah, in this one case, rho and z are both the square root of 3, and rho and z are 2. But in here, it's not that case. And in here, and in here, and notice that change in rho is really small out here near the edge of the cap, where the change in rho is the biggest when phi is 0, or when we're at that along the z-axis. So we got to do some work here is what I'm saying. We got to do some work. And the work is this. I will agree that the top part of the sphere, when I draw in these changes in rho, that top piece always ends at 2. Got it. Believe ya. But the bottom part is not always the square root of 3. Z is the square root of 3. Z is the square root of 3. Remember, Z is that coordinate system, that rectangular coordinate system. Z is just that straight up to the bottom of that thing. Z is the square root of 3, but rho isn't. We got to figure it out. And this is where your work that you had done previously will come in handy. Do you recall that z, let me put it, I'll just put it here. Do you recall that z was equal to rho times the cosine of phi? And z, we know, is the square root of 3. Believe it. But what's rho? What we want is not z here. We want rho here. What's the value of rho here, or here, or here, or here, or here? What's the value of rho in all of those places? Not the value of z. Well, if z is equal to rho times the cosine of phi, then rho is going to equal the square root of 3 divided by the cosine of phi. Beautiful. That's the relationship. Notice as phi changes from 0 to whatever rho is out here, then rho is going to change. So as phi changes, rho changes. Since z is rho times the cosine of phi, since z is square root of 3 equals rho times the cosine of phi, therefore rho will be the square root of 3 divided by the cosine of phi. That is what needs to go here. Crazy, huh? All right, now, let's think about theta for a minute. How do we think how theta changes? Well, theta is, as it was in cylindrical coordinates, as it was in polar coordinates, theta is still, from the positive x-axis, it's the amount of rotation around this way. This is what is measuring theta. If you can extend that up here, do you see how in that XY plane, because this is cutting off of a sphere, we're going to have a full revolution. I'm kind of thinking about running around the bottom of the cap of this thing, and the bottom of that cap of that thing is going to make a full circle, a full revolution. So theta is going to go from 0 to 2 pi. Phi is this angle kind of dropping down from the positive z-axis down, and I need to figure out what that would be. And so what I'm going to do to help us with that is, remember how we cut off at the square root of 3? So to kind of get the sense of this, let's imagine that z-axis hitting that plane, and let's just bring it straight across here, and let's make a right triangle. I will do that. Oops. Sorry. I will do that down over here. So z was the square root of 3 at the base of that plane, that flat plane, and I came all the way over to the edge of that sphere, the cap of that sphere. Then we've got rho right here. We've got our right angle right here. All right. Now remember, rho was 2. We had a 2 centimeter radius sphere. So we need a relationship here about this distance, that angle, or that rotation, I should say. Well, how do we figure that out? Well, let's see. This is an angle. We've got an adjacent, and we've got a hypotenuse. Cosine. The cosine of phi is equal to that adjacent side, that adjacent leg, over the hypotenuse. Now, I know you guys didn't grow up in the 80s, like 70s and 80s like I did, but when I was in school, I didn't have all the technology you have. I just had to know this one. And so I would have memorized a unit circle, and I know that the square root of 3 over 2 would have been this point over here, square root of 3 over 2, 1/2 in fact. And that angle that produced that would have been a 30-degree angle or a pi over 6 radian angle. Now, if you don't happen to have your unit circle memorized, or have some kind of a handout, I know some of you in high school or at some point along the way, you got like a sheet with all the unit circle, kind of the well-known angles like pi over 6 and pi over 4 and pi over 3. Maybe you have that somewhere, but there was the cosine of pi over 6 that produced the square root of 3 over 2. And so I know that theta, as we rotate to the edge, let me go back up here. As we rotate through angle theta to get that cap down here at z equals the square root of 3, that angle is going to be running through 0 to the angle pi over 6. And so there it is. Now some things, let me just highlight this, because this was the goal of this whole operation here, was to set up this integral. But let's just hit some highlights. Highlight number 1, dv in spherical coordinates, rho squared sine phi, d rho d theta d phi. Unit analysis, density, grams per cubic centimeter, times cubic centimeters does give you density, gives you mass in grams. Be careful that you don't kind of conflate z with rho. I mean, they do have similar values sometimes. You know, like right here, the value of rho is the square root of 3, and the value of z is the square root of 3. But if you rotate an angle, rho is at an angle now. Rho is no longer the square root of 3 to whatever. Rho is something else based on theta. So we had to do some work going back to our relationships that we found previously, that z is rho cosine phi, square root of 3 is rho cosine phi, phi is square root of 3. So depending on phi, we're going to get a different value of rho to get those shorter changes in rho, to get those more full changes in rho. So we rotate rho, turned out pi over 6. We spin that 360 degrees in terms of theta, 0 to 2 pi radians. Phi, boom, we get this thing set up. Now once it's set up, let's let Wolfram Alpha take it from there.